All right, so you were absent from class and now you need to make up what we did in class. So I want to start back with the density curve example that we ended off on last time. So the whole point here is to be able to travel from percentages to values and from values to percentages. And area is that percent. So when we were looking at A, what height should the density curve have? Well, density curves have to have area 1, or else the percentage thing wouldn't work. So this is 1/4, because this length here is 4, and to multiply the rectangle, we need to get 1, so we need 1/4. Now, to answer a question like B, we can just employ the fact that we know that this is just an area model. So what percent of time? So percent, again, is an area. Will the light flash more than 3.75, which is around there? That is a value. But we can use this area model to go back and get a percent. How? Well, let's just look at this rectangle. Its height is 1/4, and its width along the horizontal axis is 1.25, right? Because it's from 3.75 to 5. And that's about 5/4. And this is the area. So the area is just going to be the product of those, which is 5/16, which is around 31%. So we almost get this kind of look. And this only works because the area is 1, so 31% really is 31%. Okay, I'm going to erase this now. And see if I can do this. Actually using a new thing, so I don't know how to use it very well. Okay. Interpret the 38th percentile. Okay, so 38% should be somewhere in here, right? So again, we know the area this time. We know the height, but I don't know this amount. So I'll call this, I'll just call it y. So the area formula says 1/4 times y should be the area. So this amount is 1.52 by multiplying both sides by 4. So that's this amount. I call that y. So how do we answer the question, though? Well, remember that that distance really isn't the true distance. The true tick mark is somewhere past 2. So let's just say about 38% of the time, subjects will click the mouse at or before 2.52 seconds. 2.52, because there is that gap from 0 to 1 that we need to accommodate for. Okay? So that was that. Describing density curves, the mean and the median. Remember, the mean is the balance point. If it was made out of like a solid material, remember the mean is not resistant. So if we were to have a skewed density curve here, distribution, the mean would be pulled here. That's maybe a little dramatic. And the median would be back here, because the mean gets pulled towards those extreme people. The median, though, is what we'll refer to as the equal area point. It's the point that divides the area under the curve in half. This is a really good illustration of what I just said. Here's a little test for you. Which one's the mean and the median? You can pause. Here are the answers. A would be the mode. B is the median. C is the mean. Notice that the mean is closer to the extremes. This one's a trick question. A is mean and median. And here, A is the mean, B is the median, and C is the mode. Okay, and if you had like a bimodal thing, they would still both be here, but if one, peak was higher than another peak, you might have to be careful, but you're not going to really see that. But these are the main three cases. Okay. So here's just some more diagrams and pictures to help understand. So the mean and the median are the same if it's symmetric. The mean of the skewed curve is pulled away from the median in the direction of the long tail. So just other wording saying the same thing. Okay, so what's a normal distribution then? So a normal distribution is a symmetric, single-peaked, bell-shaped density curve. So we can't talk about normal distribution unless we talk about density curves because of its definition. Period. We also can call it the normal curve. It's always a capital N too, by the way. Normal distribution. And they don't have to look the same, but we measure them the same, with mu being the mean and sigma being the standard deviation. And it really is completely specified by these numbers. There are not two normal distributions that have a mean of 10 and standard deviation 1. There's just one. Okay, well, how would you describe it? Using socks. Well, the shape, symmetric, single-peaked, and bell-shaped. The center is at mu, which in this case is the mean and the median because it's symmetric. And the variability, which is the spread away from the middle, is sigma, which is the standard deviation, and it measures width or variability. Why is the normal distribution important? Well, we're going to use it later in the course. That's number one. Other reasons, they're really good approximators of like chance experiments, like rolling, probability things like rolling die or flipping coins, or even like any sort of gambling or game theory or stuff like that. Way beyond my understanding of how probability is done, but it's really, really, it also models natural things. Like, if we did a test on 1,000 people of how quickly the reaction time was when they're, stopping for a red light, it might be modeled by the normal distribution, and it'll have a mean and it'll have a standard deviation. Typically, as we do more and more and more, have more as n and gets bigger, right? Normally, data can get more and more normal, but it's not always the case that data is modeled with a normal distribution. Okay, I want to do another example. I think we'll get to this point in class. So let's definitely do this one. So we have batting average again in baseball. And we say we have a mean and a standard deviation. And we're told that it's normally distributed. So we're going to draw that bell curve. We're going to cut it in the middle. And that's where the mean's going to be. And then one tick mark over to the left and the right is where we add and subtract just one copy of sigma. Okay, so I can do that. Calculator's really nice here. And then I can go 2 standard deviations out, which is pretty significant. And that would be, and let's pause here and try and interpret. And then we could do another tick mark going 3 out, right? I'm not going to, but you could. Just for time. But so notice what's happening here. This is a really good batting average, right? Anything above 300 is pretty good, right? So we can kind of see where that number is in relation to the center and notice that, hey, that's 2 standard deviations away. The z-score for that number is 2, right? The z-score for this number is -1. The z-score for this is 0. So your z-score is now planting you a place on the normal distribution. Okay? Pretty neat. So we did a bell ringer question a little bit ago where we took the test question and I asked you, hey, can we study this plot? And we ended up kind of collecting and counting how many dots were within 1 standard deviation, which was a good majority. I think we got around like 75% or something. And we use z-scores. So basically what we said was, now with this knowledge that we have, this is plus or minus 1 standard deviation from the mean. So we just said that the area, remember this is a density curve. The area underneath is 0.75. Right? That's what we're saying by answering this question about percentages. Remember, the whole point of 2.2 is going from area and percents to values. So from going 1 plus or minus 1 z-score is a value, and we're going to a percent. You see? Oops. So it turns out, though, that now this is just data, right? If you do this enough, we get the empirical rule, which says that not 75%, but 68% of all of the values fall in 1 standard deviation left and right of the mean. So this is just done by brute force, and just, you can theoretically find this with a lot of calculations, but it's mostly by testing. Okay. So this is the empirical rule, and it just tells us what percentage values fall in. If you are looking at intervals from like -1 to 1, or -2 to 2, or -3 to 3 with z-scores. These are z-scores down here, right? So it's a very nice picture. It's pretty intuitive, and it's really applicable and usable. So we'll actually make our own tangible one in class on Wednesday, So I think this is going to be a good place to stop. We're going to use this on the board. I have some cutouts where you have scissors. We'll make some stuff so that we all know the empirical rule and use it. And we'll then take on this example. Thank you.